Hi, everyone. Welcome to Physics 151, Lecture 25, Part A. I'm going to divide Lecture 25 into two recordings to keep the video segments a little shorter. So all of Lecture 25 will correspond roughly to Chapter 9 of our textbook. Here in Part A, we're going to cover the first three sections of Chapter 9, which cover the kinematic quantities and the main kinematic equations for a rotating or spinning object. In Part B, we will move on to rotational kinetic energy, moment of inertia, and the kinematics of rolling objects. So let's start by talking briefly what we mean about when we say something that's rotating. We usually think of a relatively large extended object. We want a rigid object that will maintain its shape as it spins. And we think about it spinning about some sort of an axis that either passes through the object, like the Earth's spin axis, or these axes shown here, or the center of the propeller, or nearby. Okay, some of the axis can be offset somewhere to one side, but usually it'll be touching or passing through the object. So these objects are often symmetrical because of their very nature. We want them to be symmetrical so that way they don't jiggle around or create some sort of torque as they spin, but they don't have to be. So for example, one of the situations you're going to see often will be having some sort of a rod that's being rotated about an axis that is at the end or edge of the rod. The main thing I want us to contrast with, though, is when we think back to uniform circular motion. Uniform circular motion problems that we did a few chapters ago usually referred to small point-like objects small objects that we can pretend are like point masses because they're tracing out circles that are much larger than the object itself. So we think about, for example, the Earth going around the sun, where the size of the Earth's orbit is much bigger than the Earth. Or we think of an object tied at the end of a string and you're swinging it around in a circle that's much bigger than the object itself. So here, instead, we have an object that's relatively large, and we think of it spinning on its own axis instead of spinning through space around some other axis. The other main important difference was uniform. The word uniform in uniform circular motion referred to the fact that the speed was always constant. That speed of rotation or revolution was always constant. For these problems, we can have constant speed rotational motion, but we're also going to have a lot of problems where the rate of that rotational speed will increase or decrease over time. All right, so let's start off with some kinematic quantities. So first of all, if we take an object that can rotate, like for example, this bicycle wheel right here, and if we imagine that it has some sort of reference mark on it. So let's suppose that we take a piece of white tape or we paint a white stripe on it somewhere. Then wherever that white mark or that reference mark is, whatever angle that's located at, we can call that the angular position theta of the wheel. In trigonometry, we often like to consider when the reference point is along the positive x direction, we like to consider that to be theta equals 0. And then also in trigonometry, when you increase the value of theta in the counterclockwise direction, we usually consider that to be a positive increase in angle. And when you rotate the object in the clockwise direction, so when you change theta in the clockwise direction, we usually consider that to be a negative change in theta. The angular displacement of a spinning object is just the value of theta at any later time, like theta final, minus the value of theta at any earlier time, theta initial. So you can see that positive displacements are counterclockwise and negative displacements will be clockwise. Theta, by the way, we often think about theta in terms of degrees. So for example, here, theta final looks like it's about 120 degrees. Theta initial looks like it's about 60 degrees. However, when we go to plug our values for theta or delta theta into most of our equations, we're going to have to take those degrees or those revolutions or those cycles and convert them all into radians. That will allow our units to balance out the way they should. And I'll say a little bit more about that as we go. One of the quantities that we often like to deal with here is the path length traced out by a point on a spinning object. So if we choose any point on this bicycle wheel here, let's say it could be a point on the edge, but it could also be a point on any one of the spokes. And we follow that point through space as the bicycle wheel undergoes some sort of displacement. Okay. Then what is going to be the path length, right? In other words, the length of this sort of blue line of this arc that is traced out through space by that point on the spinning bicycle wheel. Well, we know the definition of radians from trigonometry class. It says that if you have a segment of a circle that spans theta radians, then that means that the length of the arc length divided by this radial distance r here, that ratio defines the size of theta in radians. So theta is equal to s, this arc length, divided by r, this radial distance. If I just rearrange this equation slightly, then I get that the length of the path length out there is equal to theta in radians times r in whatever distance units we want, like meters. Because the path length is in meters and r is in meters, we can see that radians must be dimensionless, and indeed they are. So while sometimes we'll write them down, right? We'll say radians or radians per second or radians per second squared. Whenever we then multiply by meters or other quantities, we can simply just remove the radians. So radians can just vanish. We can just cross them out. You could think of radians as being like a ratio, if you will, of two distances, as opposed to being intrinsically a distance themselves. All right, so that's the main reason why we use radians in all of our math equations. And you can also see that this relationship here represents the way of tying linear distance to angular displacement. So we've tied together angular quantities with linear quantities, with linear displacement. So angular displacement and linear displacement, if you will, are tied together by this relationship here. You just multiply the angular displacement by r. This is a relationship that we're going to see repeated on the later slides, the next two slides to come. All right, let's consider now how fast this wheel is turning. So that takes us to the quantity angular velocity, also known as angular speed or angular frequency. Those terms are all used pretty interchangeably. And the variable we use for that is a lowercase Greek omega. And we've already met this before when we were talking about circular motion. So if it takes this wheel a certain amount of time, delta t, to turn through this angular displacement delta theta, then we can just divide the number of radians divided by the amount of seconds, and that gives us the speed, the spin rate, if you will, of how quickly this wheel is turning. Spin rates, of course, could be expressed in degrees per second or in cycles or revolutions per second. And if you use cycles per second, we have a name for that. That's called hertz, right? But in order for us to get omega, traditionally, we need to use radians per second for the same reason that I said earlier. Radians work best with all of our mathematics and all of our formulas. So if you convert delta theta into radians, then this becomes radians per second. So we will often say, okay, if something's spinning, we'll denote that spin by writing a little sort of omega with an arrow. That just means that this object is spinning at some spin rate or spin speed, omega. Now, once again, what would happen if we followed along a little point on this bicycle wheel? Could be on one of the spokes or could be a point on the edge. And we asked the question, okay, we know that that little point on the bicycle wheel is going to be tracing out a certain distance s for every unit of time t that passes. So that means that that point on the wheel must have some linear speed through space, right? That's equal to s divided by t, the amount of time it takes. We can call that linear speed v, or v tangential. Sometimes we just call it linear speed. Sometimes we call it tangential speed. And I'll usually drop the little tan in the future. You won't see me write it very often unless I need it for emphasis, like here. When you just see a v by itself, assume that that means a linear or tangential speed of some point on the rotating body. Okay. All right, so just like in the previous slide, our relationship between the angular quantity and the linear quantity was established by multiplying by r, the radial distance from the rotational axis, the spin axis, to the point that you're interested in. So the same thing is true here, okay? In order to find out the linear speed of any point on this bicycle wheel, you just take the angular speed of the whole wheel, right? Omega is the same for the entire wheel, and you multiply by r, the distance out from the center. So notice how this looks, if I go back one slide, notice how similar that looks to this expression right here. Linear distance is equal to angular displacement times radial distance. Here it's linear speed is equal to angular speed times radial distance. And on the next slide, you're going to see a similar relationship right here for acceleration. Linear acceleration is going to be equal to angular acceleration times radial distance. So what do we mean by angular acceleration? That is, if you have some change in the spin rate over time. So suppose at some earlier time, t1, this bicycle wheel was spinning with a slower speed, omega 1. And then at some later time, t2, is spinning with a much faster angular speed, omega 2. In that case, we can see that, all right, the angular speed is changing over time. We could ask, what's the rate of change of the angular speed or angular velocity? And that is the angular acceleration. So the average angular acceleration over some time interval is just delta omega over delta t. We could also say what we could call the instantaneous angular acceleration is just alpha at any moment in time. And we're going to be doing a lot of problems where we're going to assume that the angular acceleration is constant over some period of time. So that this bicycle wheel is increasing its spin rate at some steady uniform fashion. So it's getting maybe, 3 radians per second faster every second. So that's angular acceleration. Once again, if we pick any point on the bicycle wheel while this wheel is undergoing an angular acceleration, we can also say that, hey, that point had some linear speed or linear velocity, and that linear velocity is going to be increasing over time as well. So that means we can say that it's undergoing a tangential or linear acceleration, right? Which represents that increase in v tangential as time passes. And the relationship, once again, a tangential is just equal to the angular acceleration alpha of the entire wheel times r, however far from the center of the wheel we're talking about. I should also add that what if we had a bicycle wheel that was slowing down over time, right? So suppose it had some faster angular speed at some earlier time and then some slower angular speed at some later time. Well, then when we take the delta omega, what we'll find is that there will be a negative value of alpha. So you can have an angular acceleration that points opposite to the angular speed. And that would mean that, oh, if the angular speed is counterclockwise and the angular acceleration is clockwise, then that would mean that the angular speed is slowing down as time goes on. All right. So before we summarize all of this together for constant acceleration, it's worth pausing for a moment to talk about the fact that this radial acceleration, or I'm sorry, pardon me, this tangential acceleration that we've just been discussing, right, that results from the fact that this bicycle wheel might be speeding up over time, okay, that tangential acceleration, or slowing down over time if the angular acceleration were the other way. That tangential acceleration is not the same thing as our old friend radial or centripetal acceleration, okay? If we have a bicycle wheel that's spinning even at a constant speed where alpha is 0, then every point on the bicycle wheel, right, every point on the tire or on the spokes is going to be accelerated constantly toward the center, toward the spin axis. And we know from earlier chapters that the magnitude of that centripetal acceleration for any point on this bicycle wheel is going to always be omega squared times r, or v squared over r, where this is that tangential or linear speed. That will always happen even when alpha is equal to 0. You need to maintain an inward radial acceleration on all points of the bicycle tire or spokes, etc. Otherwise, it would fly apart. Now, of course, this inward acceleration is just maintained by the structural strength of the bicycle wheel, right? However, that radial acceleration is present even when the wheel is not spinning up and not spinning down. So even when the angular acceleration is 0. And notice that the direction is always inward. It's always toward the axis. So these two accelerations are distinct, right? The tangential acceleration happens when the wheel is speeding up or spinning down, whereas the radial acceleration is always there at all times. And their directions are very, very different. So it turns out every point on this bicycle wheel could be experiencing a vector sum of two different sort of linear accelerations, if you will. Okay. This is for the rest of lectures 25 through 27, where we talk about rotation. This is the one and only and last time I'm going to mention this centripetal acceleration, this radial acceleration. From now on, if I am asking about tangential acceleration, I'm only talking about this quantity here that is tied to the angular acceleration of an object that is spinning up or spinning down. All right, so now suppose that we have, let's say, an electric fan that is increasing its angular speed over time. So that way it's undergoing some angular acceleration. Or suppose we have a bicycle wheel and it hits, let's assume it's not rolling. Let's say it's mounted on some sort of stationary axle. And suppose that you apply a brake to it. So that way the wheel slows down over time. So then that would be a constant negative angular acceleration. Okay. In any of those cases, if we can make the assumption that the acceleration is constant, so that the rate of change of omega of the angular speed is steady over time, then remember our old friends, these three equations of kinematics for constant acceleration? All three of those equations have rotational equivalence. And basically, you can prove that this is the case in the same way that we can prove that any of these equations is valid for constant angular acceleration linear motion. One way for us to remember these new rotational equations is just to take any one of these original three linear equations and substitute in the rotational equivalent for each of the kinematic quantities. So wherever you see position or displacement, substitute in angular position or angular displacement. Wherever you see velocity, substitute in angular velocity. And wherever you see acceleration, substitute in angular acceleration. So in other words, just add the word angular in front of each of these things and then replace the variable by the rotational variable that goes by that same name. The one variable that needs no replacement is time, because time is the same for linear or translational motion as it is for rotational. And then this is just a reminder of things that we already mentioned earlier. So this joins our toolbox as a parallel set of three equations that we can use for spinning objects, provided that the acceleration of the spinning object remains constant over the time interval t that we're interested in. So I'm going to do a couple of examples now, taken from my sample tutorial problems. So let's do problem number 1 and problem number 3. And then if you'd like more practice with this, you can try the other problems 2 and 4 on your own, which are pretty similar. Let me switch cameras now. Okay, so here's problem number 1 from our tutorial sheet. Suppose that there is a turntable, like an old-fashioned record player, okay? And we know that when it's at full speed, it's rotating with a frequency of 33 RPM. So remember that RPM stands for revolutions per minute. So this is an amount of sort of, angular displacement per time, revolutions divided by minutes. So we know that that is basically an angular frequency, but the units are not in the MKS units yet. So we're going to have to convert that. All right, so that'll be the final speed. That'll be omega final after we convert it. And we know that starting from rest, so omega initial is 0. it takes 1.8 seconds to get up to full speed. So the first question asks, what is the angular acceleration of the object during that time, right? And let's assume that it's going to be constant, for example, okay? And if we make that assumption that it's constant, then we can use that to calculate how many revolutions the turntable executes while it speeds up. All right, so once again, let's summarize this. We know that it starts from rest, so that means that omega initial or omega naught, we can call it either one, is equal to 0. And let's convert this. This is going to be omega final. So omega final is going to be 33 RPM, revolutions per minute. And we need to get that into our MKS units of omega. So we want to convert the revolutions into radians. Let's do that first. So we have 2 pi radians in 1 revolution. And let's convert the minutes into seconds. So we know that 1 minute is equal to 60 seconds. Right? So now it looks like I'll be left with radians per second. So I ask my calculator, what is 33 times 2 pi over 60? And I get that it's about 3.46, et cetera, radians per second. All right, so that'll be omega final. Now, notice I'm going to carry, it looks like it's going to be about a two significant figure problem. So we want to make sure that we carry at least one extra sig fig for any intermediate values like omega final here, right? Until we get to a final answer. And then we'll round down to just 2 sig figs. All right, now finally, let's answer the question. What is the angular acceleration, which is what we're after? All right, well, I think I can use, this is still a continuation of part A. I think I can now use one of our equations for angular acceleration. I can either say average angular acceleration over time is equal to change in omega over change in t. Or if I wanted to make the assumption of constant acceleration already, I can say omega final is equal to omega initial plus alpha times t. In either of these cases, I know the time and I know the initial and final omega. So that will allow me to solve for alpha. In fact, these are really the same equation, is really what they are. So let's go ahead and use this first equation up here. This is going to be omega final minus omega initial divided by delta t. So that's going to be 3.46 minus 0 divided by 1.8 seconds. And I ask my calculator what that is, and I get 1.92 radians per second squared, right? Radians per second. It looks like it's a 2 sig fig problem. So if I wanted a final answer, I would round to 2 sig figs. Looks like the answer is B. However, if I'm going to use this value for alpha in part B of the problem, I really should go back and use the value that has the extra significant figures on it. All right, so I'm not going to bother solving this a second time with the other equation, because like I said, those equations are basically the same. Let's go on to part B. Part B asks, how many revolutions does a turntable execute during this time? So if we were to look down on the turntable from above, what would we see? We would see that as it starts from rest and then gets up to full speed, that we would see that the turntable will execute some number of revolutions, right? So what we would like to know is what is that angular displacement? So the angular displacement, when we first calculate it from our formulas, will be in radians, and then we can convert that radians into revolutions as requested. Okay. All right, so let's do that. Let's use our equations for kinematics. And when I think about my 3 equations for kinematics for constant acceleration, I want to pick one of the 2 that has angular displacement, so that way I can solve for that, and for which I know everything else. So one option is for us to use the second equation, which says that theta minus theta naught, so I'll just call that delta theta, is equal to omega naught times t plus 1/2 alpha t squared. I know the time from up above, 1.8 seconds. I know alpha because I found it in the previous part, in part A. And I know omega initial was 0 because the turntable starts from rest. So it looks like, yes, equation 2 would let me solve for what I want. Okay. The other option would be for us to use equation 3. Or let's take a look and see if that will work. Omega final squared is equal to omega initial squared plus 2 alpha delta theta. I know omega final is 3.46. Omega initial was rest. And alpha, again, I calculated up above. So this one would also work. So either one of these two equations would work just fine. Just for simplicity, let's go ahead and use my first choice, which is equation 2. Delta theta is equal to 1/2 alpha t squared, 1.92. Notice I'm putting that extra significant figure back in. And then the time is 1.8 seconds. And don't forget to square it. And then I asked my calculator what that answer is, and I get about 3.1 radians. All right, now notice that that is the final answer for the angular displacement. All we need to do now is convert it from radians into revolutions. So let's do that. So 3.1 radians, let me just write it again, 3.11 radians times 1 revolution is equal to 2 pi radians. That'll cancel my radians. And after I ask my calculator what that is, I get about 0.495 of a revolution. So now we can look back and say, all right, our initial values here were 2 sig fig values. So let's round that off to 2 sig figs, about 0.50 of a revolution. It's like part A, answer A is the correct answer. Okay, let's take one more example problem. Let's take a look at example problem number 3. Suppose that we have a wheel with a diameter of 40 centimeters. Now, I usually don't give diameters in my problems. I usually give radius because that's one of the values that's the easiest to overlook and forget that it's a diameter instead of a radius. So I don't want to try and trip up any students on purpose like that. However, I do want to warn you, our textbook loves to give diameter values instead of radius values. So you have to just read every problem carefully and remember to cut it in half when necessary. Okay, so this is a 20 centimeter radius wheel, just to be clear. Okay. All right, and suppose that it accelerates. Now, this wheel is mounted on a stationary axle, so it's not rolling yet. This is not a rolling problem. It's just mounted on some axle that's fixed in space, and it spins up, right? So it spins up from an initial rotational speed of 240 RPMs, which I've already converted for you into angular speed in radians per second, and it spins up to 360 RPM, which we'll call omega final. And the time it takes to do that is 6.5 seconds. So I ask a couple of questions, okay? While that spin up occurs, what is the linear acceleration of a point on the edge of the wheel? So now this is going to be the tangential acceleration that we're asking for right here, right? I'm not asking for that centripetal acceleration or radial acceleration, right? And through what total distance in space does a point on the edge of the wheel travel during those 6.5 seconds? Okay. All right, so let's go ahead and take a look at the at part A first. All right, we know that in order to find the linear acceleration A tangential, the easiest way for us to probably do that would be to, if we pick a point on the edge of the wheel, so that means this is going to be the value for R up here. In order for us to do that, it would be useful for us to find the angular acceleration of the entire wheel and then just multiply by the distance of that point that we're interested in from the spin axis. So in this case, that'll become the radius of the entire wheel. Okay. So now let's calculate what this angular acceleration is for the entire wheel, and then we can plug that in. All right, well, let's think about our equations for angular acceleration. One formula we could use is the definition of angular acceleration, which is change in angular speed divided by time. And I think that might work well. Here's the initial and final angular speed, and there's the time. Okay. Or we could use omega final is equal to omega initial plus alpha times t. And that's essentially the same equation, right? Because we know omega final, we know omega initial, and we know t. And so we could solve for alpha there. So either way, it works. So let's go ahead and calculate what this is. This is omega final minus omega initial over delta t. Using the values from up above, 37.7 radians per second minus 25.1 radians per second. Divide by the time, 6.5 seconds. And I ask my calculator what that is, and I get about 1.94 radians per second, so radians per second squared. So that's my intermediate value for the angular acceleration of the whole wheel. Now we can go back to the point at the edge of the wheel and say that the tangential acceleration of that point is going to be equal to the angular acceleration of the whole wheel times the distance from the spin axis to that point on the edge of the wheel that we're interested in. So that's going to be equal to 1.94 radians per second squared times 20 centimeters. Okay, so once again, I convert that into meters, keeping everything in MKS units. And I ask my calculator what that is. And that turns out to be about, I'll just continue on to the right here, about 3.88 meters per second squared times radians. But remember, radians is dimensionless. So this is one of these cases where we can just poof, evaporate it, and we don't need to keep writing it down. Okay. And then I can round that off to 2 sig figs. If this were going to be a final value, 3.9. All right, now let's consider part B. Part B is asking, suppose that we follow along that point on the edge of the wheel during the entire 6.5 seconds during this spin up period. And we want to find out what's the total linear path length through space that point on the wheel traces out during this spin up time. So we know that, okay, from one of our earlier slides, that path length, that arc path length is going to be equal to the angular displacement of the wheel during that time period times the radial distance from the spin axis to the edge of the wheel. So once again, we're interested in this quantity here. So let's find that first. So how am I going to get that? And then I can plug it in. Well, if I look at my 3 equations for kinematics for constant acceleration, once again, 2 of them contain theta, they contain delta theta, right? Or theta and theta minus theta initial. So one of those is equation number 2. So that's equation number 2, right? Do I know everything else in here? Well, looks like I do. Time is given up above as 6.5 seconds. Angular acceleration, we already found in the previous part. And initial angular speed, we are given in the problem, right? Or if I wanted to, I could consider using equation 3. And the same thing is true. We know all of these other quantities now, either because they're given in the problem or because we calculated alpha up above. So either one of these could be used to find the angular displacement. Let's use the first one. Now this time the wheel does not start from rest. So we have this initial angular speed of 25.1 radians per second. And then I have my angular acceleration that I calculated in part A. And then I ask my calculator what this is, and I get about 204 radians. So now I can plug this into our initial equation again. So that's going to be equal to 204 radians times 20 centimeter radius wheel, okay? And that turns out to be 40.8 meters. So once again, radians is dimensionless. So radians times meters is just meters. All right. All right, this looks like the answer should be 2 sig figs. So let's round that off to just 41 meters. Answer choice D. So those are a couple of examples of using our kinematics equations for rotation. And notice that these are a little more complex than the kinematics equations for translational motion or linear motion, but not a lot. They're not vastly different. Right? We're basically using equations in the same way. The only thing that makes these a little more complicated is the stranger units, right? The more unfamiliar units, and the fact that people like to use degrees and revolutions or cycles and radians. So we have to often switch back and forth between those over and over. And also keep an eye out for diameter versus radius in a lot of these problems. All right, so that's it for part A. And I'll pick up with part B of the lecture with a little theory about moment of inertia and rotational kinetic energy. And then we'll solve some example problems for that and for rolling objects.